Hello everyone, welcome to OHM Institute. I am Surendra Reddy, Faculty for Electrical Machines at OHM Institute. So welcome to the series on GATE previous year questions. So this is fourth lecture in our series. In the first two lectures, I discussed about previous year questions on synchronous machines subject. In the third lecture, I discussed about 1 mark questions related to transformers. And in this lecture, I am going to discuss about 2 marks questions related to transformers, and we are covering from gate 2011 to 2023. Okay, so 13 years of question papers we are considering, and I am going to discuss about 2 marks questions from transformer subject. So we have the first 2 marks question, that is from gate 2013 question paper. Okay, so read the problem. The following arrangement consists of an ideal transformer and an attenuator, which attenuates by a factor of 0.8. An AC voltage VW1. See here you have a diagram. You can see on the primary side we have two terminals WX. On the secondary side there was a rheostat available and there was a tapping, and the output terminals are YZ. So now in the first case, what was happened? An AC voltage of 100 volt is applied across WX. Okay, so the first voltage is applied across WX. To get an open circuit voltage VYZ1, that is across YZ. That means supply voltage was given to WX terminals and output voltage was measured at YZ terminals. Okay, right. Next case. Now we have one more case. In the next case, an AC voltage of VYZ2 equal to 100 volt applied across YZ terminals to obtain an open circuit voltage of VWX2 across WX terminals. That means, see, very simple point. First case, voltage was applied on the left side and output voltage was taken across YZ. But in the second case, voltage was obtained or applied on the YZ terminals to obtain voltage across WX terminals. Okay. So what is the ratio between VYZ1 by VWX1 and VWX2 by VYZ2? Okay. So it's a complex problem where your aptitude skills are more important rather than your technical skills. Okay. So you have to understand the problem carefully. There is an attenuator available. First we need to understand what does mean by an attenuator. So attenuator is simply nothing but a rheostat. Okay, suppose if you consider there was a resistance available, okay, and imagine I connected a 100 volt voltage across this resistor. Okay, therefore obviously 100 volt will drop across the resistor. Now if I take tapping for this resistor, imagine I took the tapping exactly at the center. If I take the tapping exactly at the center, we know voltage will uniformly distribute across the resistor. So tapping at center means obviously output voltage will become 50 volt. Therefore 100 volt was compressed to 50 volt. Therefore attenuation factor is 0.5. Suppose if the tapping was taken at 80%, output voltage will become 80 volt. Therefore attenuation factor is 80%. That is what is meant by attenuation. Okay, and the same attenuator is used even in this particular question also. You can understand there was a rheostat available here and tapping was taken, and it was clearly mentioned the attenuation factor is 0.8. That means the tapping was taken at 80%. So let us solve this problem. Now, so I will redraw the diagram again. Just see the transformer that was given. This is the primary side of the transformer. Terminal W, terminal X, and here we have the secondary winding of the transformer, and the secondary was connected to a rheostat, and the rheostat was taken tapping here exactly at 80% because attenuation factor is 0.8. So this is YZ terminals, and the turns ratio of the transformer was clearly mentioned. You can see the turns ratio is 1:1.25. That is the turns ratio. Okay, so the turns ratio is 1:1.25. And in the first case, what was happened? An AC voltage of 100 volt was applied here. See, a 100 volt source was applied. This is 100 volt. This is what they are calling it as first case VWX1. Okay, that one indicates first case, and the voltage was applied between W and X. Now, according to turns ratio, if I give 100 volt as input, definitely how much voltage will come as the output here. Okay, so you can easily understand 125 volt will come because it's a step up transformer. But there was an 80% attenuation. Out of this 125, how much will appear across YZ terminals? Because attenuation is 80%, therefore output voltage is 0.8 into 125. Can I say 0.8 into 125? That is nothing but 100 volt only. Therefore, the voltage that we are getting between YZ terminals, okay, that is VYZ, and this is the first case, so VYZ1 is equal to 100 volt. Okay, so I am giving 100 volt as input, and final output is also equal to 100. Therefore, what is the first ratio, guys? Yes, the first ratio VYZ1 by VWX1, that is 100 by 100. So 100 by 100 means option B it is available, option C also available. Therefore, A and D are already ruled out. Now we have to answer the second case also. In the second case, what was happened? Next time, an AC voltage of 100 volt is applied between YZ terminals. This time the voltage was applied across YZ terminals to get open circuit voltage across WX terminals. So let me draw the circuit once again. Okay, see that. So now we have a transformer again. This is WX, and here we have the other winding which is connected to the attenuator or rheostat. There was 80% tapping, and here we have Y and Z, and the turns ratio was 1:1.25. Okay, this was the transformer, but this time voltage was connected across YZ terminals. Here the source was connected. What is the source voltage? Clearly mentioned, 100 volt. This is known as VYZ, second case YZ2, let's say. Okay, now if I give 100 volt here, how much voltage will be obtained across WX terminals? Most importantly, WX terminals are open circuit. You have to measure the voltage here. That is the answer I need. Okay, so how to answer this? Very simple. As I am giving 100 volt here, so the first question is how much voltage will appear here? If I know this voltage, definitely using a turns ratio, I can transfer this voltage to this side. I will get the answer. So your first question is, what is this voltage is going to be? See, the common mistake is, as the attenuator ratio is 0.8, most of the students, they will believe that, sir, this voltage will become this time 100 divided by 0.8. That is absolutely wrong. Okay, why? Because remember guys, resistance is a material which can only step down the voltage, it can never step up the voltage. Resistor cannot step up the voltage. Resistor means always voltage drop takes place, voltage rise cannot take place. If a resistance or rheostat was really able to step up the voltage, I will replace all the transformers in power systems with rheostats only. What is the need to use high cost transformers if rheostats were really able to step up the voltage? Definitely not possible. See, even though there was an 80% tapping here, output voltage remains equal to 100 only. Why? Because you see, for this transformer, as a supply was given here, can I say this winding is a secondary winding? Right now the secondary winding is under loaded condition or no load condition? No load condition. That's why the current passing through secondary is equal to 0. If a secondary current is equal to 0, then what is the primary current? Also 0. There will be small no load current. I am neglecting it. Consider the transformer is ideal. Therefore, primary current is also equal to 0. If a primary current is equal to 0, indirectly, what is the current passing through this small portion? This is 20% portion, because 80% tapping is there. What is the current passing through this 20% portion? Indirectly 0. If current passing through this 20% portion is 0, then what is the voltage drop across this portion? Yes, the voltage drop across this portion is 0. Okay, but what is the voltage applied across the remaining 80% winding? You see, this is a supply voltage 100. Can I say the same 100 will appear here according to KVL equation? So the upper half, this voltage is 0, but the lower half voltage is 100. Then what is the final voltage across this entire rheostat? 100 volt. Okay, So if this is 100 volt, how much will come here? According to turns ratio, can I say this will become 100 by 1.25? 100 by 1.25 means the answer will be equal to 80 volt. Therefore, the voltage that we will get between Wx, that is VWx, it is the second case 80 volt. What is the voltage I applied here? 100. The same 100 will reflect here because there is no voltage drop here. Suppose in case if this current is a finite value, maybe let us say you got a voltage drop, let's say 5 volt here. If a 5 volt drop takes place, you will get a 95 volt here. Understand? But right now the current is 0, voltage drop is 0, so entire 100 will appear here. This 100 looks like a primary voltage of the transformer. Therefore, the secondary voltage will be 100 by 1.25 according to the turns ratio. The voltage is equal to 80. Now, what is the answer we need in the second case? According to the question, I need VWx2 divided by VYZ2. Okay, and what is the answer we got? VWx2 80, VYZ2 100. So the answer is 80 by 100. So 80 by 100 means, can I say it is available in the second option? Therefore, third option is also wrong. Understand? All right, let's move to the next question. This is the question in GATE 2014 question paper. Okay, so let's read the problem. The load shown in the figure absorbs 4 kilowatt at a power factor of 0.89 lagging. You can see the diagram. The transformer input voltage 220, output voltage 110. Assuming the transformer to be ideal, the value of reactance X to improve the power factor to unity. What is the value of reactance X? This X value we have to find out so that the power factor can be improved to unity. Understand? Okay. So most importantly, the transformer is ideal. Therefore, no load current is neglected. See how to proceed this problem. Very simple. You see that load is drawing some current, right? This I2. First, our duty is to find out this I2 because the load active power was given, load power factor was also given. So definitely this I2 will have active component as well as reactive component. Okay. Now using the turns ratio, you can see 220 by 110 volt transformer means the turns ratio is 2:1. Using this turns ratio, transfer this reactive component to the primary. Okay, let's say that is I1 dash. Now if that reactive component is compensated by this reactance X, then overall input power factor can be unity. Okay, let's see how to proceed. Okay, first our duty is find out the load current. Okay, you see that what is the load power given? The load power is equal to, I can write V2 I2 cos phi 2 active power. Now the power is 4 kilowatt, that is 4000 watt. Yes, output voltage is 110 volt. I2 I don't know, but power factor we know. What is the power factor? 0.89 lagging. So from this you will get I2 magnitude, isn't it? So what is the value of I2? So I2 will be equal to 4000 divided by 110 into 0.89. So I am getting 40.85 ampere. 40.85 ampere. But I need to represent this current with angle also because the power factor is 0.89 lagging. What is the power factor angle? Phi 2 will be equal to cos inverse 0.89. Okay, that means the angle will be equal to cos inverse 0.89. So 27.12 degrees. So how to represent I2 now? Therefore, I2 is equal to 40.85 at an angle minus 27.12 degrees. Why I am using minus angle? Because it is a lagging power factor. Lagging power factor means current will lag the voltage by finite angle. Okay, fine. Now transfer this current I2 to the primary side. We know I1 dash is always equal to K times of I2, where K is N2 by N1. N2 by N1 or V2 by V1 both are same. Therefore, V2 is 110, V1 is 220 into I2 40.85 at an angle minus 27.12 degrees. Therefore, you will get the magnitude of current now. Okay. So 110 by 220, that is by 2. 40.85 divided by 2. So that is 20.4 425 at an angle minus 27 degrees, sorry, minus 27.12 degrees. Okay, this is I1 dash. What is I1 dash first of all? Can I say I1 dash is nothing but the current drawn by primary due to the load? Yes, that is I1 dash. So now if I draw the circuit once again, okay, so remember, let me divide this current into, rectangular format. Yes, the real part will be 18.17 minus J 9.31. So this is rectangular format of representation. Now let us draw the circuit. Okay, coming to the circuit, here we have the source voltage 220 volt given, and the internal resistance of the source is 1 ohm. Now there is a reactance X here. Okay, and here we have the load. The load is transferred to the primary sub. Now, what is the load current? That load current is nothing but I1 dash. We just found what is the real part and imaginary part. Real part 18.17, imaginary point 9.31. 18.17 minus J 9.31 ampere. Now the point is, what should be the current drawn by this reactance part? If I know the current drawn by this reactance, let's say Ix, then I can find out the total input current I. What is our aim? Our aim is the total input current must be unity power factor current. Can I say power factor will be unity only when reactive component nullified? Therefore, this minus J 9.31 must be nullified by this Ix. That means Ix will be equal to plus J 9.31. Okay. Suppose if Ix is plus J 9.31 and I1 dash reactive component is minus J 9.31, can I say both will nullify each other? Then I will have only real part and power factor will be equal to unity. Therefore, Ix is equal to plus J 9.31 ohm. See, current is plus J 9.31 means it must be a capacitor. Therefore, the reactance must be a capacitor. Okay, capacitor, then only current will be plus J 9.31. Therefore, what is reactance? X is equal to, yes, voltage across the reactance, that is 220, divided by what is the current carried by reactance? 9.31. Understand? Okay. So if I solve it, this will be minus J 23.63 ohm. That is going to be the reactance value. So that what will happen? Entire input power factor will be equal to unity. Understand? So very simple. Transfer the load current to the primary side. Make sure that reactance or imaginary part is nullified or reactive part is nullified. If reactive part is nullified, entire input power factor becomes unity. Reactive part is nullified only if minus J 9.31 is compensated by plus J 9.31 here. That means this X must be a capacitive element. Okay, and the reactance will be minus J 23.63 ohm. Okay, that is the answer. All right, let's move to the next question. This is a question from GATE 2014 paper. So read the problem. The parameters measured for a 220 volt by 110 volt 50 Hz single phase transformer are: self inductance of the primary 45 millihenries, self inductance of the secondary 30 millihenries, mutual inductance between primary and secondary 20 millihenries. Using the above parameters, what are the values of leakage inductance and magnetizing inductance referred to primary side in the equivalent circuit respectively are what? So these are the values we have to find out. See, first of all, primary self inductance was given for us, secondary self inductance was given for us, along with that mutual inductance is also given, and we are asked to find out leakage inductances on primary and secondary, and also we have to find out magnetizing inductance referred to primary side. All values must be referred to primary side. So let us see how to calculate all of them. First of all, we need to understand that in a transformer there will be two fluxes. One is mutual flux, which will link both primary as well as secondary. Suppose if this is the primary winding of the transformer and here we have the secondary winding of the transformer, there will be a flux which will link both of them. Okay, the flux which will link both of them, this is what we call it as mutual flux. Along with mutual flux, there will be one more flux available known as leakage flux. Primary leakage flux will link only primary winding. This is primary leakage flux. Secondary leakage flux will link only secondary winding. This is secondary leakage flux. Therefore, what will happen? Now, because of the leakage flux, there will be an inductance in the primary side. That is what we call it as primary leakage inductance. Let's say L1. Similarly, because of the secondary leakage, there will be an inductance in the secondary side, that is L2. These are the inductances due to leakage flux. At the same time, primary side, we have a mutual flux. That mutual flux will create an inductance known as magnetizing inductance. Okay, this is known as magnetizing inductance. Let's say Lm. Okay, all right or not? And apart from them, similarly secondary side also we have magnetizing inductance, and between the two there will be mutual inductance also. Understand or not? Between primary and secondary. Now, if you look at the primary side, how many inductances are present overall? 2 inductances. One is due to leakage. Yes, one is due to leakage. Another one is due to mutual flux. Combination of these two is what we call it as total primary inductance L1. So, L1 is the total inductance on the primary side, which is a combination of leakage inductance as well as magnetizing inductance. Similarly, the total inductance on the secondary is equal to L2. L2 is total inductance on the secondary. It is a combination of leakage inductance as well as magnetizing inductance. So, what are L1 and L2 values given for us already? See, self-inductance of the primary is already given. This is nothing but L1 value. Primary inductance L1. Self-inductance of the secondary was also given. This is nothing but L2. Total secondary inductance L2. And along with that, we have a mutual inductance between primary and secondary, that is M. Using these 3 values, we have to find out leakage inductances as well as magnetizing inductance. Okay. Now, you need to understand very clearly what is the difference between self EMF and mutual EMF. Self EMF means it is the EMF in a given winding due to the current carried by same winding. But mutual induced EMF means it is the EMF induced in a winding due to the current carried by other winding. Okay, I will apply this concept to find out leakage values of both windings. Okay, so if I apply KVL equation here, what is the total inductance L1 is equal to leakage inductance plus magnetizing inductance. Okay, so primary side I am doing first. Primary side. Yes, total inductance L1 is equal to leakage inductance on primary plus magnetizing inductance on primary. Okay, our aim is to separate leakage inductance. Therefore, leakage inductance is equal to total inductance on primary minus magnetizing inductance on primary. Already in the given question, total inductance was given 45 millihenries. Therefore, to find out leakage inductance, I have to find out magnetizing inductance. How can I write? Yes, L1 minus magnetizing inductance is due to which flux? Mutual flux. And what is the formula for inductance of any winding? Self-inductance formula N phi by I. L formula is simply N phi by I. Okay. As it is a self-inductance, you have to use self-current. Okay. So therefore, see, magnetizing inductance. This is a primary winding inductance. Therefore, I have to use a primary number of turns. Due to which flux? Mutual flux divided by current carried by primary winding. Okay. So this is leakage inductance of the primary. So in order to find out leakage inductance, I have to separate this mutual flux. Okay. Now I can separate that mutual flux using one more inductance given in the problem, that is mutual inductance, M. Tell me what is mean by M? It is mutual inductance representing mutual EMF indirectly. What is the definition for mutual EMF? Suppose primary side I wanted to calculate mutual EMF. Can I say primary mutual EMF is equal to the EMF induced in primary winding, but due to the flux created by secondary current. What is secondary side mutual EMF? It is the EMF induced in secondary winding due to the flux created by primary winding current. Therefore, I am writing right now mutual inductance with respect to primary winding. Okay, with respect to primary winding is number of turns in primary winding into, yes, mutual inductance is due to mutual flux, right? Number of turns in primary winding into mutual flux, but which current I have to use? Yes, mutual induced EMF in primary winding is due to the current carried by secondary winding. So I have to use I2 here. You understand? So that is the difference between magnetizing inductance and mutual inductance, guys. Magnetizing inductance is a self-inductance. Therefore, primary number of turns, primary current. But mutual inductance is due to the other winding current. Primary number of turns, but current is due to secondary current. Okay. Now separate phi m from this formula. Therefore, phi m is equal to m I2 divided by n1. Substitute that phi m here. So if I continue, L1 is equal to L1 minus N1 by I1 into what is the phi m is equal to M I2 by N1. Now what happens here? So N1 will cancel. Then what is the final formula? Yes, L1 is equal to L1 minus I2 by I1 times of M. If I go to the next page, L1 is equal to L1 minus I2 by I1 times of M. Can I say I2 by I1 is nothing but V1 by V2? So this is V1 by V2 times of M. So what is the total inductance on the primary given? Yes, total inductance on the primary is 45 millihenries. According to the question, if you go back to the question, V1 by V2, 220 by 110. 220 by 110. And what is the mutual inductance given? Yes, mutual inductance is given as 30 millihenries or for 20 millihenries. I will go back. Sorry, mutual inductance is 20 millihenries. So mutual inductance is 20 millihenries. Therefore, if I solve it, 45 minus 2 into 20, 40. Therefore, primary leakage inductance will be equal to 5 millihenries. Okay, this is the primary leakage inductance. In a similar manner, can you find out a secondary leakage inductance? Yes, what will be the same equation, guys? If I rewrite this equation similarly, I need not to derive again. So secondary leakage inductance similarly, I can write secondary leakage inductance L2 is equal to secondary total inductance L2 minus V1 by V2 M or V2 by V1 M. Yes, this time it will be V2 by V1 times of M. Okay. So what is the total secondary inductance given already in the problem? 30 millihenries. V2 by V1, that is 110 by 220 into mutual inductance is 20. 30 minus 110 by 220 into 20. Therefore, this is 20 millihenries. This is secondary leakage inductance referred to secondary side, guys. But in the question, we are asked to find out secondary leakage inductance referred to primary side. Therefore, we have to transfer secondary leakage inductance to primary side. That is L2 dash. As we are transferring to primary side, it will be N1 by N2 whole square times of L2. That is 220 by 110 whole square times of 20. So it is 4 into 20, that is 80 millihenry. This is secondary leakage inductance referred to primary side. So what is the primary leakage inductance? 5 millihenries. This is already referred to primary. This is a secondary leakage inductance but referred to secondary, and I transferred it to primary, that is 80 millihenry. But according to the question, we have to find out one more parameter. What is that? Magnetizing inductance also I have to find out. To find out magnetizing inductance, you just draw primary side. Yes, everything we have to find out referred to primary. So this is the total inductance on primary L1. This is the leakage inductance on primary L1. This is magnetizing inductance on primary Lm. So what is the total inductance? L1 is equal to leakage inductance plus magnetizing inductance. From that, what is magnetizing inductance? Total inductance minus leakage. What is the total inductance on primary? 45. So this is 45 minus, what is the leakage inductance on primary? We found 5 millihenries. Therefore, the answer is 40 millihenries. That is the magnetizing inductance on primary. So finally, what are the answers? primary leakage inductance we got yes, primary leakage inductance we got 5 millihenry. Secondary leakage inductance referred to primary 80 millihenry, and overall magnetizing inductance is 40 millihenry. So 5, 80, 40. That means second option is the correct answer. All right, let's move to the next question. This is also the question given in GATE 2014 paper. The previous two questions are also from GATE 2014 paper only. So read the problem. Yes. An open circuit test is performed on 50 Hz transformer using variable frequency source, keeping V by F ratio constant to separate its eddy current loss and hysteresis loss. The variation of core loss per frequency as a function of frequency is shown in the below figure. The hysteresis loss and eddy current loss of the transformer at 25 Hz respectively are how much? So first of all, it was open circuit test data. It was clearly mentioned. Okay. And it is performed keeping V by F ratio constant. We know this is a mechanism to separate hysteresis loss and eddy current loss. Yes. To separate hysteresis loss and eddy current loss, open circuit test has to be conducted for a number of times, keeping V by F ratio constant, and every time we have to change the frequency. And then draw a graph between iron loss divided by frequency on y-axis and frequency on x-axis. Therefore, if you draw the curve like this, by taking frequency on x-axis, iron loss by frequency on y-axis, it will be like a straight line intersecting y-axis. And what is this intersection point? Yes, this is nothing but constant A, and the slope of this line is nothing but constant B. Yes or not? So what is indirectly what is the intersection here? That is 10. So therefore, constant A is equal to 10. And what is the slope of the line, guys? That is constant B. Okay, what is the slope of the line? Change in y-axis 15, 10. Therefore 5 divided by change in x-axis 50 Hz. That is 1 by 10. That is constant B. So once we know constant A and constant B, what are the formulas for hysteresis and eddy current loss? Yes. If V by F ratio is constant, the formula for hysteresis loss is equal to A into F. What is A value in the graph? 10. At what frequency we are asked to find out hysteresis and eddy current loss? 25 Hz. Therefore, 10 into 25. So hysteresis loss is equal to 250 watt. Similarly, what is the formula for eddy current loss? Eddy current loss is equal to B into F square. In the given question, B we got 1 by 10. Frequency square, that is 25 square. This will become 62.5 watt. So hysteresis loss is 250. Eddy current loss is 62.5. Therefore, the correct answer is second option. 250 watt is a hysteresis loss, 62.5 watt is eddy current loss. Okay, so this is open circuit test and separating hysteresis loss and eddy current loss. Okay, all right. So we have the next question. This is from GATE 2015 question paper, 2 marks question. Just read the problem. A 3-winding transformer is connected to AC voltage source as shown in the figure. The number of turns are as follows. So see, primary winding has N1 number of turns and N1 is equal to 100. This is a second winding, N2 number of turns, 50. This is the third winding, N3 number of turns, 50. Okay, so this is like 2:1:1 transformer. If the magnetizing current is neglected and the current in the two windings are 2 at an angle 30 degrees ampere, that is I2, I3 2 at an angle 150 degrees ampere, then what is the value of current I1 in the primary? Very easy question. These two currents are separately given. Just transfer them to the primary side and add both of them. Okay. So if I2 is transferred to primary side, it will become I2 dash. Okay. What is the formula for I2 dash? I2 dash is equal to N1 by, sorry, we are transferring to primary side, right? So we know current ratio is inversely proportional to turns ratio. That means I1 by I2 is equal to N2 by N1. Okay, so therefore I2 dash is equal to N2 minus N1 times of I2. What is N2 by N1? 50 by 100. What is I2 given in the problem? 2 at an angle 30 degrees. Therefore, what is the answer? 1 at an angle 30 degrees. This is going to be the current I2 dash. Similarly, transfer this I3 to the primary side, its value will become I3 dash. So in a similar manner, what is I3 dash formula? I3 dash is equal to N3 by N1 times of I3. So therefore, N3 by N1, 50 by 100 into I3, how much is I3 given? 2 at an angle 150. So if you solve it, it will become 1 at an angle 150 degrees. This is I3 dash. Now I have I2 dash and I3 dash. Add both of them, you will get the total current primary. Actually, you should have I0 also on the primary side, but that I0 is neglected already. Okay, so therefore, so 1 at an angle 30, 1 at an angle 150. So total primary current I1 is equal to I2 dash plus I3 dash. So I2 dash is 1 at an angle 30 degrees. I3 dash is 1 at an angle 150 degrees. It looks like two equal phasors with how much phase angle difference? 30 degrees to 150 degrees, 120 degrees difference is there. When any two equal phasors are added with 120 degrees phase angle difference, summation will be same magnitude with the intermediate angle. The intermediate angle is 90 degrees. Okay, always remember A at an angle 0 plus A at an angle 120. If you add both of them, equal phasors, 120 degrees difference, summation remains the same, but angle will be intermediate angle. 60 degrees will come. Similarly, another shortcut. A at an angle 0 plus A at an angle 60 degrees. When any two equal phasors are added with 60 degrees phase angle difference, summation will be root 3 with intermediate angle. Okay. If there is 90 degrees, you will get root 2 with intermediate angle. Okay, like that. If there is 180 degrees, summation will be 0. Or else, if you don't remember these, simple calculations, at least expand this polar form into, rectangular form. Add square root of real part square plus imaginary part square, and angle will be tan inverse imaginary part by real part. So what I did here is that very simple. As no load current is already neglected, just transfer load components to primary side. Okay. Always remember I1 by I2 is equal to N2 by N1. Using that relation, transfer secondary current to primary current. Add both responses together, you will get the overall response. Okay, simple question. So the answer is 1 at an angle 90 degrees. So option A is correct. All right, let's move to the next question. Read the problem. A balanced three-phase AC voltage source is connected to a balanced star-connected load through a star delta transformer as shown in the below figure. The line-to-line voltage rating is 230 volt on star side and 115 volt on delta side. If magnetizing current is neglected, that means indirectly the no load current is neglected. Magnetizing current is neglected. IS is equal to 100 at an angle 0. IS means this one, guys, load current. 100 at an angle 0. Then what is IP? IP is primary line current is the question mark. Secondary line current was given and primary line current is the answer we have to find out. Okay, right. So load is balanced very clearly. Every phase has same resistance. So secondary line current was given. We are asked to find out what is primary line current. And if you look at the transformer, primary is a star connection, secondary is a delta connection. Primary line voltage 230, secondary line voltage is 115. Okay, so if I redraw the diagram again, primary is a star connection. Okay, primary is a star connection. This is the given star connection on the primary side. Secondary is a delta connection. Secondary is a delta connection. Okay, and this delta connected transformer is connected to a star connected balanced load. Most importantly, the load is balanced. If the load is balanced, obviously the currents are also going to be balanced. Now coming to the voltages, primary side line voltage 230, secondary side line voltage 115. Okay, so primary side line voltage is 230, secondary side line voltage is 150. That means what will be the turns ratio of the transformer? You see, primary side line voltage 230, therefore phase voltage will be 230 by root 3. Okay, secondary side line voltage 115, so phase voltage is also 115. That means the turns ratio is 230 by root 3 is to 150. Okay, All right, that means 2 is to root 3 indirectly. Anyway, now secondary side line current was given. What is the secondary side line current? 100 at an angle 0. Can I say that 100 at an angle 0 is the line current for the delta? Line current is 100 at an angle 0 means what will be the phase current? Phase current. Yes, we all know that in a delta connection, phase current will always lead line current by 30 degrees. Phase current will always lead line current by 30 degrees. Therefore, as the line current is at an angle 0, definitely phase current will be at an angle plus 30 degrees. Coming to the magnitude, phase current will be 1 by root 3 times of line current. Okay, so line current is 100, therefore phase current will be 100 by root 3 at an angle 30 degrees. Imagine this phase current is equal to I2, secondary side. I am assuming primary side phase current is equal to I1. What is the ratio we know? I1 by I2 is always equal to N2 by N1. From this I1 is equal to N2 by N1 times of I2. What is N2 by N1? N2 by N1 means 115 by 230 by root 3. So therefore 115 divided by 230 by root 3. And what is I2? 100 by root 3 at an angle 30 degrees. Therefore can I say this root 3 and this root 3 will cancel? So what is the final answer will be? Yes, the final answer is 115 into 100 divided by 230 at an angle 30 degrees. Okay, this will be primary phase current I1. So if I solve it, 115 into 100 divided by 230. So I am getting 50 at an angle 30 degrees amperes. This is the primary side phase current, guys. But the answer that we need, what is the primary side line current? Okay, but we know in a star connection, phase current and line current will be same. Therefore, if phase current is 50 at an angle 30, line current will also be equal to 50 at an angle 30. Okay, that means this will be the line current as well. The answer is 50 at an angle 30. See, this is a valid discussion because the load is balanced, guys. Suppose if the load is imbalanced, these relations will not going to hold. Okay, you'll get a different calculation. In that case, every phase we have to calculate, okay, separately, or else you have to draw positive sequence, negative sequence and zero sequence diagrams, and then you have to add all the responses to get the total response of the entire input line current. Okay, but fortunately the load is balanced. So very simple thing, in a delta connected circuit, if line current is at an angle 0, phase current will lead the line current by 30 degrees. Okay, so phase current will lead the line current by 30 degrees. And the same 30 degrees will follow in the primary side. This is going to be the answer. So the answer is 50 at an angle 30. So option A is correct. Okay. All right, let's go to the next question. This is a question from GATE 2015 paper. Okay, so read the problem. A 200 by 400 volt 50 Hz 2-winding transformer is rated at 20 kVA. Its windings are connected as an auto transformer of rating 200 by 600 volt. A resistive load of 12 ohms is connected to the high voltage side of the auto transformer. What is the value of equivalent resistance seen from the low voltage side? Very simple. Actually, it was a 2-winding transformer, 200 by 400 volt. But it is connected as auto transformer of 200 by 600 volt. Okay, how auto transformer connection looks like? So 200 by 600 volt, it's a step up auto transformer. Therefore input voltage is 200 volt. Here you will give 200 volt as a source voltage. Therefore this is a 400 volt winding and the output voltage will become 600 volt. Okay, now across this 600 volt a resistance was connected. A resistance was connected, and what is the resistance value? 12 ohm is connected. A 12 ohm resistance is connected. Now what is the question? If you transfer this 12 ohm resistance to the primary side from the low voltage side, what is its value? That's the question. Okay, what is the value of this resistance referred from LV side? Is it answered? What is the value of equivalent load resistance seen from low voltage side? That means you have to all the way transfer that resistance to the primary side. So very simple, guys. In a transformer, what is the basic concept behind transferring the parameters? Yes, even though you transfer the parameter from primary to secondary or secondary to primary, the amount of power drawn by that resistor should not change. Yes or not? Is it the same concept we use it to discuss in transformer? If a secondary winding resistance transferred to primary or primary winding resistance transferred to secondary, the copper loss in that resistor should not change. That means indirectly, the power drawn by the resistor should not change. What is the power drawn by this resistor? Can I say power drawn by this resistor is equal to V square by R? What is V square by R? 600 square by 12 watt. Now even if I transfer that resistance to LV side also, it has to consume the same power. Okay, so see that LV side means what is the voltage? 200, and imagine that resistance value R becomes R dash. Now I need to find out this R dash value. Now tell me, what is the power consumed by this R dash? Is it 200 square by R dash? 200 square by R dash. V square by R is the power drawn by resistor. Now this power and the previous case power must be same. Even if I transfer the resistor, the power drawn by that resistor should not change. Therefore, 600 square by 12 must be equal to 200 square by R dash. Therefore, 600 square by 12 must be equal to 200 square by R dash. From this, what is R dash value is equal to, yes, 200 by 600 whole square times of 12. Okay, is it nothing but 1 by 9 times? 1 by 9 into 12. Okay, so what is the answer? So the answer is 1.33 ohm. So that is the resistance value referred to which side? LV side of the transformer. Okay, simple rule. Whether the resistance is referred to LV side or HV side, it has to consume the same amount of power. That is the basic principle of a transformer, right? Okay. Any calculation mistakes, please try to adjust them. Okay, hope I am doing correct calculations, but the concept you need to understand. Okay, right. Okay, so the next question we have, this is also from GATE 2015 question paper. So read the problem. Two three-phase transformers are realized using single-phase transformers as shown in the below figure. What is the phase difference between V1 voltage and V2 voltage? Okay, there are two transformers you can understand. The first transformer, this is a delta connection. Clearly you can understand. Secondary is also a delta connection, isn't it? Whereas coming to the second transformer, primary is a delta connection, but secondary is a star connection. And on the secondary side, first transformer line voltage V1, second transformer line voltage V2. We are asked to find out what is the phase angle difference between these two voltages. Okay. Whereas on the primary side, you can understand first transformer primary and second transformer primary, both are connected in parallel, isn't it? You see the line A of first transformer, line A of second transformer connected to the same bus bar. Okay. Therefore, all are connected in parallel. Line B of first transformer, line B of second transformer connected to the same bus bar. Line C of the second transformer, line C of the first transformer connected to the same bus bar. Therefore, they are connected in parallel. As a primary side, they are connected in parallel. Their line voltages are in phase with each other. Suppose first transformer line voltage is, let us say, V at an angle 0. Second transformer line voltage is also V at an angle 0. Line voltage. Now this is delta or star, guys. Delta, we know in delta, if line voltage is at an angle 0, what about phase voltage? Phase voltage will also be at an angle 0 degrees. If primary phase voltage is at an angle 0, can I say secondary phase voltage also at an angle 0? Because phase voltages will not have any difference. Now secondary is a delta or star? Delta. In delta, if phase voltage is at an angle 0, what about line voltage? Also at an angle 0, because phase voltage and line voltage are same. If you are confusing, I will redraw the diagram. See, first transformer is a delta by delta transformer. Okay, but a second transformer is a delta by star transformer. Delta by star transformer. And if you also see the terminology, how the terminology was, on the secondary, output terminal is A2, B2, C2. Even for the second transformer also A2, B2, C2. Primary side, output terminals A2, B2, C2. Even for the second transformer also A2, B2, C2. The terminals are same. Okay. here A2, A2, and this is B2, B2, this is C2, and this is C2. Output terminals are A2, B2, C2. But primary side, the two transformers are connected in parallel, therefore their line voltages are same. Let's say this is V at an angle 0, this is also V at an angle 0. Both line voltages are same because they are in phase with, they are connected in parallel. If line voltage is at an angle 0, what about primary phase voltage also at an angle 0 only? If primary phase voltage is at an angle 0, can I say secondary phase voltage, let's say V dash. Secondary phase voltage V dash, this is also at an angle 0. Because primary phase voltage, secondary phase voltage are always in phase with each other. If a secondary phase voltage is at an angle 0, secondary line voltage will also be at an angle 0 only. Because it's a delta, in a delta line voltage and phase voltage both are same. So finally, V1 is at an angle 0 degrees. But coming to the secondary, primary line voltage at an angle 0, therefore primary phase voltage also at an angle 0. If primary phase is at an angle 0, secondary phase is at an angle 0. Yes or not? But secondary is a star connection. If phase voltage is at an angle 0, can I say line voltage will be equal to root 3 times of phase voltage at an angle plus 30 or minus 30? Yes, plus 30 degrees. We know in a star connection, line voltage will always lead phase voltage by 30 degrees. Line voltage will lead the corresponding phase voltage by 30 degrees. Therefore, if phase voltage is at an angle 0, line voltage will be at an angle 30 degrees. So indirectly, can I say this is nothing but V2? So what is the phase angle difference between V1 and V2? You can see 0 degrees and 30 degrees. The phase angle difference will be equal to 30 degrees. Therefore, the answer is 30 degrees. 30 degrees. Understand? Okay, simple. So simple point. Primary phase voltage, secondary phase voltage, both are in phase. But line voltages may have angle difference that depends upon whether it is a star connection or delta connection. All right, we have the next question. This is a question paper. This is a question from GATE 2015 paper. Read the problem. Two single phase transformers T1 and T2, each rated at 500 kVA, are operated in parallel. Percentage impedance of T1 and T2 are 1 plus J6 and 0.8 plus J4.8 respectively. To share a load of 1000 kVA at 0.8 lagging power factor, the contribution of transformer 2 is the answer we need. So first of all, you need to understand both transformers are equally rated. What is the rating of each transformer? 500 kVA. As both transformers are equally rated, no need to convert these per unit impedances into a common base kVA. Generally, what we will do, if per unit impedances or percentage impedances are given, convert both impedances onto a common base kVA rating, and usually we will take larger transformer as a common base kVA. However, in this problem, as both transformers are equally rated, no need to convert them again into common base kVA. Okay, so what is Z1 given per unit value? It is 0.01 plus J 0.06. Z2 per unit impedance. Z2 is equal to 0.008 plus J 0.048 per unit. And what is the total load power? The total load power, or you can say better right, S load. S load is equal to 1000 kVA at 0.8 power factor lagging. Now we need to find out what is the contribution of T2, that too in volt ampere power only. kVA contribution we need to find. Yes. How to find out in a parallel combination what is the sharing of a second transformer? Yes. It is equal to total load into opposite impedance Z1 by total impedance Z1 plus Z2. What is the total load? 1000 kVA directly into Z1. What is Z1? 0.01, 0.06. 01 plus J 0.06 by Z1 plus Z2. 0.01 plus J 0.06 plus 0.008 plus J 0.048. So if you solve this, you will get the kVA sharing between kVA sharing of second transformer. Don't No need to consider angle at all. Why? Because we are asked to find out only kVA rating. In case if we are asked to find out what is the power factor of the second transformer, then I have to take here kVA at an angle, power factor angle, then you will get power factor as well. Okay, so if I solve it, normally gate calculator do not have complex mode, so you have to separately calculate real part, imaginary part, then take the ratio. Okay, but I have a manual calculator with me, I'm directly calculating. Okay, so I'm getting 555.55 kVA. Okay, so please check this calculation and just verify. Okay, I am getting 555.55 kVA. Okay, suppose if I am asking you to calculate what is the load shared by first transformer, then total load power into Z2 by Z1 plus Z2, opposite impedance by total impedance, that will give you the correct answer. Okay, all right, let's move to the next question. This is a question from GATE 2016 paper. Okay, so read the problem. A single phase 22 kVA 2200 by 200 volt 50 Hz distribution transformer is to be connected as an auto transformer to get an output voltage of please make a small correction, this should be 2400 volt. Its maximum kVA rating of auto transformer is, okay, see, the given two winding transformer is 2200 on one side and 200 volt on other side. Okay, so this must be converted into an auto transformer to get an output voltage of 2400 volt. What is the maximum kVA rating possible? So therefore, what are the possibilities? So if I wanted to get 2400 volt on the output side, definitely both voltages must add. Okay, I need a step up auto transformer connection. So in the first connection, suppose if I take 2200 volt as the input voltage, then definitely this will be 200 volt winding and output voltage becomes 2400 volt. So what is the ratio K of auto transformer? K is always defined as low voltage by high voltage of auto transformer. Okay, what is the low voltage value? 2200, high voltage value 2400. So it will be 11 by 12. That is the ratio K. There is another possibility available. Okay, suppose if I give input voltage 200 volt, let's say I am giving input 200 volt and the other winding is 2200 volt. Once again, the output is equal to 2400 volt. The required condition is satisfied. What is the condition we need? Output voltage must be 2400. But what is the ratio K here? K is equal to low voltage 200 by high voltage 2200. So the value K is equal to 1 by 12. But question is about maximum kVA rating. What is the maximum kVA rating possible from auto transformer? We know maximum kVA rating is possible at higher K value or lower K value. Definitely at higher K value, because what is the formula for VA rating of auto transformer? Yes, VA rating of auto transformer is equal to 1 by 1 minus K times of VA rating of two winding transformer, isn't it? Therefore, maximum VA rating is possible at higher K value. So out of the two possibilities, higher K value will be definitely 11 by 12. Therefore, if I substitute 1 by 1 minus 11 by 12 into what is the two winding transformer kVA rating? Yes, 22 kVA. The two winding transformer kVA rating is 22 kVA. So if I complete this, I will get 12 into 22. Okay, so that would be the answer for total kVA rating. Okay, so it will be equal to 20 into 12, 240, 240 plus 24, 264 kVA. So that would be the maximum kVA rating possible. Okay, all right, let's see one more question. This is a question in GATE 2016 paper. So a single phase 2 kVA 100 by 200 volt transformer is reconnected as an auto transformer such that its kVA rating is maximum. Okay, the new rating in kVA is how much? So very similar question compared to the previous one. First of all, what is the two winding transformer? 100 volt 200 volt. it is converted as an auto transformer. As I mentioned, when we are converting two winding transformer to auto transformer, two possible connections are there, but we have to make sure that K is higher value. Okay, so that is possible if I give 200 volt winding. So for 200 volt winding, we are going to give the input. Therefore, 100 volt winding will be here. And what is the overall output voltage becomes 300 volt. Okay. So what is the value K now? K is LV by HV, where LV is nothing but 200, HV is nothing but 300. So K is 2 by 3. If K is 2 by 3, what is the VA rating of auto transformer? 1 by 1 minus K times of VA rating of two winding transformer. So if I substitute 1 by 1 minus 2 by 3 into what is the VA rating of two winding transformer? 2 kVA. So I think you will get 3 times of 2, which is equal to 6 kVA. So the answer will be 6, isn't it? Okay. 1 minus 2 by 3, that is 1 by 3. 1 by 1 by 3, 3 times 3 into 2, 6 kVA. So the maximum kVA possible is 6 kVA, isn't it? All right. So let's see one more question. This is a question in GATE 2016 paper. Let's read the problem. 3 single phase transformers are connected to form delta star 3 phase transformer of 110 kV by 11 kV. The transformer supplies at 11 kV a load of 8 megawatt at 0.8 power factor lagging to a nearby plant. Neglect the transformer losses. The ratio of phase currents in delta side to star side. What is the answer we need? Delta side to star side phase current ratio is required. First of all, what is a delta star transformer is given, right? Primary is delta, secondary is star. Okay, secondary is star. Now, what is the voltage rating? 110 kV on primary side, 11 kV on secondary side. Obviously, they are line values. So, input line voltage 110 kV, output line voltage is 11 kV. Okay, then find out what is the turns ratio. I need what is the turns ratio. We know turns ratio is always phase voltage ratio or line voltage ratio, phase voltage ratio. So tell me what is primary side phase voltage? Line voltage 110 kV. Therefore, can I say phase voltage is also 110 kV because it is delta. Line value, phase value both are same. Coming to secondary star connection, line voltage 11 kV. Therefore, what is the phase voltage? 11 by root 3 kV. Therefore, what is the turns ratio? Yes, I can go to the next page. The turns ratio N1 by N2 is equal to primary phase voltage 110 kV, secondary phase voltage 11 by root 3. So therefore, the answer will be root 3 into 10. This is primary to secondary phase voltage ratio. But what is the answer I need? The answer that we need is current ratio. What is the ratio of phase currents in delta side to star side? See, delta side phase current, let's say I1, star side phase current, let's say I2. What is I1 by I2 is the question. Okay. So the answer that we need is I1 by I2. I1 is delta side phase current, I2 is star side phase current. This is the answer we need. But we know in a transformer, I1 by I2 is always equal to N2 by N1. So I1 by I2 is equal to N2 by N1. So what is N2 by N1 from here? 1 by 10 root 3. That's all. So this is delta side phase current to star side phase current ratio 1 by 10 root 3. That means what is the answer? 1 by 10 root 3. So option A is correct. So this ratio is independent of load. See, even though load power factor was given, you need not to consider them. Why? Because whatever may be the load, the ratio doesn't change. Magnitudes of the currents may change, but primary to secondary current ratio does not change. Same current ratio will come. So that is 1 by 10 root 3. That is 1 is to 10 root 3. Okay. All right. Let's move to the next question. This is a question from GATE 2017 paper. Just read the problem. A 3-phase, 3-winding delta star 1.1 kV by 6.6 kV by 400 volt transformer is excited from AC mains at 1.1 kV side. See, supply was 1.1 kV side. Okay. It supplies 900 kVA load at 0.8 power factor lagging from 6.6 kV winding. 300 kVA load at 0.6 power factor lagging from 440 volt winding. The RMS value of the line current in ampere drawn from 1.1 kV winding is how much? So very simple question. There are three windings, guys. This is the primary winding. This is the primary. This is 1.1 kV side. And there are two more windings. Secondary is a delta. This was connected to a load. How much load? 900 kVA load. 900 kVA, 0.8 lagging power factor load. There is one more winding which is a star connected winding, and this is connected to one more load, and the load power is 300 kVA at 0.6 lagging power factor. Okay, so it's a transformer having three windings. First winding connected to source, second winding connected to load, third winding is also connected to load. So as there are two loads available, what I can do, I can simply apply superposition theorem. Therefore the total demand will be equal to sum of the two loads. And we know in a transformer, output volt ampere power and input volt ampere power both are equal to same. So therefore I can write input volt ampere power is equal to output volt ampere power, right? Output volt ampere power. But output, two loads are there. First load 900 kVA, but 0.8 lagging power factor. 0.8 lagging power factor means what is the power factor angle? 36.86. Therefore, minus 36.86 plus what is the other load? Another load that is connected is 300 kVA at 0.6 lagging power factor. Therefore, this is 300 at an angle 0.6. 0.6 means what is the angle? Cos inverse 0.6. So 53.13. So these are the two loads that are connected. So I have to add them both vectorially. So 900 at an angle minus 36.86, 300 at an angle 53.13. Add both of them, you will get the resultant power. Okay. So if I add both of them, so I am getting 1190.95 at an angle minus 40.90 degrees. So therefore, the total input kVA will be equal to 1190.95 kVA. Okay. Input kVA means, can I write root 3 V1 I1 simply? Because it is a three-phase transformer, therefore obviously root 3 VL IL formula I have to use. And what is the line voltage on the input side? 1.1 kV. Therefore, I can calculate what is I1. So I1 will be equal to 1190.95 divided by root 3 into 1.1. See, this is also K, voltage is also K. That K and K will cancel. Therefore, you will get the answer. So the input line current will be 625.08 ampere. That is going to be the input line current. Very simple, two loads are there, add both of them, but as the kVA ratings were given, add vectorially. The power factor angle will play a major role here. Understand? Okay, let's see the next one. If the primary line voltage rating is 3.3 kV star side of a 25 kVA star delta transformer, the per phase turns ratio is 5:1, then the line current rating of the secondary side is how much? What is the line current rating of the secondary side? First of all, the given transformer connection is a star delta. So primary is a star connection. Okay. Secondary is a delta connection. Secondary is a delta connection. Assume primary line voltage is V1 and secondary line voltage is V2. And what is the primary line voltage already given? 3.3 kV. Okay, so primary side, the voltage is equal to 3.3 kV. And what is the turns ratio? 5:1. See, turns ratio is 5:1. We know turns ratio is always a phase voltage ratio or line voltage ratio, phase voltage ratio. Now see, input side line voltage V1. So what is the phase voltage will become? Is it nothing but V1 by root 3 or 3.3 by root 3? Output line voltage is V2. Therefore, what is the phase voltage? Also V2 because it is delta. Therefore, 5:1 is equal to the ratio between V1 by root 3 and V2. So therefore 5:1. 5 by 1 is equal to ratio from V1 by root 3 and V2. From this you can separate V2 value. So that is equal to 1 by 5 into V1 by root 3. So 1 by 5 into what is V1? 3.3 kV by root 3. So this will give you output line voltage. So 0.381 kV. This is going to be the output line voltage V2. So once I know output line voltage V2, I can apply volt ampere rating, because input volt ampere rating or output volt ampere rating both are same. So what is the formula for VA rating in a three-phase transformer? Root 3 V2 I2. V2 is the secondary line voltage, I2 is the secondary line current. So root 3 into what is the secondary line voltage? 0.381 kV, that is 381 volt into I2. And what is the VA rating given? Yes, the VA rating of the transformer is 25 kVA. Just a substitute. So 25 kVA means 10 power 3. So you will get the answer for output line current. If I substitute 25 kV divided by root 3 by 381, so I am getting 37.88 ampere. So this is going to be the secondary line current. So very simple problem. Almost you solve any number of questions in three-phase transformers. So you need to be careful about relation between line voltage, phase voltage, line current, phase current, turns ratio. So turns ratio is always defined as phase to phase ratio, not line to line ratio. Okay. So what is the line current rating of the secondary side? I2 is the answer we need, and I found using this formula. Okay. So 37.88. Clear? Okay, let's try to answer one more question. This is a question from GATE 2018 paper. So read the problem. A three-phase 900 kVA 3 kV by root 3 kV delta star 50 Hz transformer has primary high voltage side resistance per phase of 0.3 ohm and secondary low voltage side resistance per phase of 0.02 ohm. Iron loss of the transformer is 10 kilowatt. The full load percentage efficiency of the transformer operating at unity power factor is how much? Okay, so question is very simple. We are just asked to find out full load efficiency at unity power factor. But to calculate efficiency, first we need the information of iron loss as well as copper loss. Iron loss was straight away given. Iron loss of the transformer is 10 kilowatt. So our duty is to find out copper loss, but to find out copper loss, I have to find out current rating of the transformer, because resistances were already given. So what is the connection given? Delta star, right? Primary is a delta connection. Secondary is a star connection. Okay. Now winding resistances are already given. What is the winding resistance? Primary side, high voltage side, resistance is 0.3. So primary side resistance of each winding is 0.3 ohm. Secondary side, the resistance of each winding is 0.02 ohm. If you know resistance value, how to find out copper loss? I square into R, but the machine is a three-phase machine, so you have to multiply with 3 I square R. So I need what is the current passing through every winding in primary as well as in secondary. If I know that, I can easily answer. Remember, this is resistance per phase. As both are resistances per phase, you need current passing through each phase. I need phase current, not line current. What is the VA rating? 900 kVA. Voltage rating 3 kV by root 3 kV. I need phase current. What is the formula for VA rating with phase currents? When you have a phase values available, the formula will be 3 V phase into I phase. Understand? Okay. So if I proceed further, so primary side first. VA rating is equal to 3 times of V phase into I phase. So from this, I phase is equal to V volt ampere rating by 3 times of V phase. What is the volt ampere rating? 900 kVA divided by 3 times of. Tell me, primary side, what is the phase voltage, guys? As primary is a delta connection, phase voltage, line voltage both are same, that is 3 kV. Okay, so 3 kV 10 power 3. So if you solve it, you will get 100 ampere, isn't it? 10 power 3 will cancel. 3 into 3 9, 900 by 9 is equal to 100 ampere. So this is primary phase current, guys. If you know primary phase current, what about copper loss in primary? Copper loss in primary side, that is 3 I1 square into R1. So 3 into 100 square into what is the resistance on the primary side? 0.3. So if you solve it, 9000 watt. This is primary side copper loss. Similarly, you can find out a secondary side copper loss also. Okay, same formula. Once again, VA rating is equal to 3 V phase into I phase. From that, I phase is equal to VA rating divided by 3 V phase. What is the VA rating? 900 kVA divided by 3 into, yes, what is going to be the phase voltage on the secondary side? Secondary is a star connection, guys. On star side, line voltage √3. Okay, if line voltage is √3, what is the phase voltage? √3 by √3, 1 kV. Okay, so therefore secondary side phase voltage is equal to 1 kV. So 10 power 3 will cancel. 900 by 3, this is 300 ampere. Then find out copper loss in secondary. Copper loss in secondary, this is equal to 3 I2 square into R2. So 3, what is I2 secondary side phase current? 300 square into, what is the resistance on the secondary side? I forgot. Secondary side resistance 0.02, right? 0.02. Just to solve this, so 3 into 300 square into 0.02. So I am getting 5400 watt. Therefore, what is the total copper loss? Total copper loss means you have to add both. What is the primary copper loss? 9000. Secondary copper loss 5400. 9000 plus 5400, 14400 watt. Now you have a full load. That too, this is full load copper loss, guys. Most important thing is this is a full load copper loss. Why this is a full load? Because I am using rated currents, right? I am using a KVA rating. Rated KVA rating means rated current I am getting. Rated current means this is definitely this is a full load copper loss. Now we have a full load copper loss with us and full load iron loss also with us. Then what is the formula for efficiency at full load? Yes. Now full load efficiency. Yes. What is the formula for percentage efficiency at full load? So that is VA rating into cos phi 2 divided by VA rating into cos phi 2 plus iron loss plus full load copper loss multiply with 100. Okay. So what is the VA rating? 900 kVA. I am substituting everything in kilo. At what power factor we are asked to find out efficiency? Unity divided by 900 kVA unity power factor plus what is iron loss? In the question data it was clearly mentioned 10 kilowatt, 10K plus full load copper loss we just found 14.4K. So into 100, this will directly tell you what is percentage full load efficiency. So if I calculate 900 plus 10 plus 14.4, yes, I am getting 97.36%. Yes, that is going to be the full load efficiency of the given transformer. So when winding resistance was given, how to solve the problem? See, resistance is always, resistance or reactance, anything is always expressed per phase. As resistance was expressed per phase, you need current also per phase. If you need line current, you can use √3 VL IL formula. but I need phase current. That's why I'm using a 3 V phase I phase formula. Using this formula, I got phase current, and I separately calculated primary copper loss and secondary copper loss. Then I will get total copper loss. Then I can solve the problem. Suppose in the question, if I modify, calculate what is half load efficiency of the transformer, then copper loss will change. You cannot use 14,400. This is full load copper loss of the transformer. Therefore, half load copper loss means you have to multiply with 1 by 4, because we know half load copper loss is 1 by 4 times of full load copper loss, right? Okay, iron loss doesn't change. Okay, let's see one more problem. This is a question from GATE 2019 paper. Read the problem. A single phase transformer of rating 25 kVA supplies 12 kilowatt load at a power factor of 0.6 lagging. This is the first load. The additional load at unity power factor that we can add so that the transformer does not exceed its rated kVA. The transformer does not exceed its rated kVA. That is the question. So first of all, what is the rating of the transformer? 25 kVA. The rating of the transformer is equal to 25 kVA. Okay. Now, what is the load already existed? The already existing load is equal to kilowatt was given, right? What is already existing load? 12 kilowatt. 12 kilowatt at how much power factor? 0.6 lagging. Yes or not? Now, what is the extra load? What is the extra load that we can add? Okay, what is the extra load that we can add at unity power factor such that VA rating of the transformer does not exceed? So what we have to do first convert this kilowatt rating to kVA rating. Then assume this extra kVA is equal to something called X. Add both of them vectorially so that the maximum value should be equal to 25 kVA only. So convert this 12 kilowatt to kVA rating. What is a kVA rating? kVA rating is equal to kilowatt divided by power factor. So therefore, so we have two loads now. Load number 1. 12 kilowatt divided by power factor 0.6, isn't it? Therefore, it is equal to how much? 12 kilowatt divided by 0.6. This is indirectly 20 kVA at 0.6 lagging power factor. 0.6 lagging power factor, isn't it? That means with respect to angles, how can I write? 20 at an angle 0.6 power factor means what is the power factor angle? 53.13. I'm not doing conjugate, guys. If you do conjugate, you'll get plus 53.13. That doesn't matter anyway. Okay. What is the new load? This is load number 2. I don't know what is a new load. That is the answer I have to find out. I'm assuming, let's say, some X kVA. X kVA, but this is at which power factor? Unity power factor. Unity power factor means X at an angle 0 degrees indirectly. Now, these are the two loads that we are adding to the transformer so that the overall rating should not exceed transformer nameplate reading. Okay. So, therefore, what is the total load now? Total load is equal to 20 at an angle minus 53.13 plus X at an angle 0. If I add both of them, I should get the magnitude 25. I don't bother about angle, okay? This angle is not required for me. I need the magnitude. If I add both of them, the magnitude should not exceed 25 kVA. That is what? The overall load does not exceed transformer rating. Power factor, I am not bothering about it, okay? That depends upon the angle that we are going to get. So, how to achieve this? Therefore, if I separate this is a polar form, separate into, rectangular form. So, you will get, so therefore, see, 25 at a different phase angle you will get, I am assuming phi is equal to 20 at an angle minus 53.13 plus X at an angle 0. Okay, therefore if I separate 20 cos 53.13, 20 cos 53.13, is it nothing but active power 12 kilowatt minus j 20 sin 53.13, that is equal to 16. Okay, plus x at an angle 0 means only real part will be there. So what is the overall real part? 12 plus x minus j 16. Okay, this is 25 at an angle phi. I don't bother about phi at all. Okay, so now I can equate the magnitude. 25 is equal to square root of 12 plus x whole square plus 16 square. And if I solve, I will get that x value, that is the extra kVA load, so that transformer does not exceed its rating. Okay, so if I solve it, okay, 7.20. See, the common mistake most of the students will do is that already 12 kilowatt load is there, that means its kVA rating is 20, already 20 kVA load is there. So what is the extra load we can add means they will simply say 5 kVA, because transformer overall power rating is 25. Sir, already 20 kVA is there. Sir, I will add extra 5, overall will become 25. That is wrong. You cannot add kVA ratings or kVA values algebraically. The angle is very important. The power factor angle is important. Two active powers can be added algebraically, two reactive powers can be added algebraically, but you cannot add 2 volt ampere powers algebraically. Okay, the angle is important. So the second load is unity power factor load, so that's why it is at an angle 0. First load is at 0.6 power factor load, the angle is 53.13. Okay, so that is how we understood that we can add 7.20 kVA additionally at unity power factor, so that transformer overall rating will be equal to 25. Okay, that's it. All right, let's move to the next question. This is a question from GATE 2021 instrumentation paper. Read the problem. A single phase transformer has a maximum efficiency of 98%. Core losses are equal to 80 watt and equivalent winding resistance seen from primary side is 0.5 ohm. The rated current on the primary side is 25 ampere. What is the percentage of the input current at which maximum efficiency occur? Okay, see, it was clearly mentioned maximum efficiency 98%, and core losses are also mentioned. What is the core loss value? 80 watt. And winding resistance seen from the primary side, that is R01. Okay, see the information given, iron loss is equal to 80 watt. Total resistance referred from the primary side is 0.5 ohm. Okay, we know at maximum efficiency, copper loss value is equal to iron loss value. Am I correct? What is a copper loss formula? Let's say current is I, or else I1 square R01 should be equal to iron loss value. This is at maximum efficiency. Therefore, already resistance was given. What is the resistance value? 0.5. Iron loss value is equal to 80 watt. Okay. From this, I1 is equal to root over 160, isn't it? Let me calculate it. So therefore, the value of current is 12.64 ampere. That means this is the current at which maximum efficiency is created. But what is the rated current of the transformer? 25 ampere. That means 12.64 ampere is how much percentage of 25 ampere is the question. Okay, so therefore X, that is the load at which maximum efficiency is created, is equal to 12.64 divided by the rated current 25. Okay, so how much will be this? Yes, this is equal to 0.505. So percentage value, if you need 50.5%, therefore maximum efficiency is created at 50.5 percentage of full load. Okay, so therefore the answer is 50.5. So nearest option A. Okay, so simple. Maximum efficiency means copper loss is equal to iron loss. As the resistance was already mentioned, I calculated what is the current at which maximum efficiency is created, and that current is how much percentage of rated current. That is what the question is. Okay, so I compared this 12.64 with rated current 25. That is going to be the percentage. Okay, simple question. All right, let's try to answer the next question. This is a question from GATE 2023 paper, 2 marks question. Read the problem. when the winding CD of the single phase 50 Hz two winding transformer is supplied from an AC current source of a frequency 50 Hz, the rated voltage of 200 volt 50 Hz is obtained at the open circuited terminals AB. Okay, so the voltage that was measured at AB terminals is 200 volt. 200 volt is measured here. Okay. Next, the cross sectional area of the core was given, average core length is given, maximum flux density was given, relative permeability was given, leakage impedance of both primary and secondary windings were given. Okay, I'm not reading them, but their leakage impedances were given, right? Okay, the leakage impedances was given for both winding AB as well as winding CD. Next, considering the magnetizing characteristics to be linear, that means saturation is neglected, and core losses are also neglected. We are asked to calculate what is the self-inductance of winding AB. This winding AB, what is the total self-inductance is the question. We know self-inductance is equal to leakage inductance as well as mutual, or you can say magnetizing inductance. Okay, so first we will try to calculate magnetizing inductance. Leakage inductance you can find out from leakage impedance. Okay, leakage impedance will have leakage reactance. Reactance is equal to 2 pi f into L. So if I divide reactance with 2 pi f, I will get leakage inductance as well. So first find out magnetizing inductance. So what is the formula for magnetizing inductance? L, magnetizing inductance is equal to N square by R, where R is known as reluctance of the magnetic medium. Okay, so let us first find out reluctance. If I know reluctance, I can easily find out magnetizing inductance. Okay, we will calculate number of turns later. First, let us focus on reluctance. What is the formula for reluctance of the magnetic core? It is equal to length of the core by mu naught into mu r into cross sectional area. Okay, or length by mu into cross sectional area. What is the length of the core given? Yes, it was given length of the core. Okay, the length traversed by the flux 500 millimeter. So the length of the core is 500 millimeter, that is 10 power minus 3 meters, divided by mu naught is equal to 4 pi into 10 power minus 7. And what is the relative permeability? Relative permeability is 5000. Okay, so relative permeability 5000. And what is cross sectional area of the core? Yes, cross sectional area of the core, yes, 5000 millimeter square. Okay, that is 5000 into millimeter square means 10 power minus 6. Millimeter 10 power minus 3, square is 10 power minus 3. So if I simplify this, I will get reluctance of the magnetic core. Okay, let's calculate it. Okay, so I'm getting 1.5915 into 10 power 10. Okay, so this is going to be the reluctance value I am going to get. Okay, so keep it aside, reluctance value. Then I need a number of turns, but to calculate number of turns, we have voltage information, right? So what is the voltage information given? Yes, voltage across winding AB is 200 volt. Okay, so using this voltage information, I can find out number of turns. Okay, what is the formula for voltage? So I will do it in the next page. Voltage across winding AB is equal to 4.44 Bm cross sectional area frequency into number of turns. So voltage was 200, 4.44. What is the flux density given? If you see, the flux density given is 1 Weber per meter square. Okay, right. So flux density is 1 Weber per meter square. Cross sectional area 5000 mm square. That is the cross sectional area. So that is 5000 into 10 power minus 6, frequency 50 Hz. I don't know the number of turns, so we need to calculate number of turns. Okay, so if I do that, so 200 divided by 4.44 into 5000 into 10 power minus 6 into 50. So I am getting 180.18. 180.18 means you can take approximately 180 or 181 turns. Okay, 180 or 181 turns, because number of turns should be always integer number. So use that number of turns in the previous calculation, you will get magnetizing inductance. Therefore I'll take a different color. So the magnetizing inductance will be equal to N square. So I'm taking 180 square divided by reluctance 1.5915 into 10 power 10. So guys, I made a small mistake in the calculation. So this is actually 15915. Okay, I made a small mistake in the calculation. This is 15915, not 10 power 10 is not there. So that's a calculator mistake. So I will cover this 15915. Okay, anyway, now I can calculate the magnetizing inductance. Okay, so 180 square divided by 15915. So I'm getting 2.0358 henries. Okay, that means if I convert into millihenries, 2035.8 millihenries. Okay, so that is going to be the magnetizing inductance. But for this magnetizing inductance, I have to add leakage inductance also. What is the leakage inductance of winding AB? For winding AB, see that the leakage impedance of winding AB, first one. Okay, you can see this is the leakage impedance, where 5 is the resistance, and this is going to be the leakage reactance, 100 pi into 0.16. Okay, 100 pi into 0.16. So for winding AB, the leakage reactance is 100 pi into 0.16 ohm. But I need leakage inductance. Therefore, what will be the leakage inductance? Leakage inductance is equal to reactance divided by 2 pi f. Isn't it? Where frequency is 50 Hz. So it is 100 pi into 0.16 divided by 2 pi into 50. Okay, pi will cancel, 2 will cancel for 50 times. So it is 50 into 0.16 divided by 50. 0.16 henries. 0.16 henries means, can I say 160 millihenries? Therefore, finally, what is the answer? Magnetizing inductance is 2035.8. Leakage inductance is 160. Therefore, what is the total self inductance? Therefore, total self inductance L is equal to magnetizing inductance plus leakage inductance. Magnetizing inductance 2035.8, leakage inductance 160. So if you add both of them, 2035.8 plus 160, so the answer will be 2195.8 millihenries. This is the answer, 2195.8 millihenries. Okay, that's all. And with this, I completed the 2 marks questions in the previous GATE examination papers. Almost we have 20 questions approximately in 13 years of papers. That means you can expect more than 1 2 marks question in GATE examination. Okay, at least 1 2 marks question from transformers. Sometimes even 2 marks questions may also come. Okay, questions are very much based on fundamentals only. There are no tricky or difficult questions in the past 10 years of papers, but fundamentally you need to be strong so that you can answer the questions easily. Okay, thanks for watching.